Hello, and welcome. Take a moment and look around you. The lights illuminating your room, the computer or phone you're watching this on, the refrigerator humming quietly in your kitchen, all of them are powered by an invisible, silent force. This force is electricity, but not just any kind. It's a special, dynamic type of power that we call alternating current, and it's all thanks to something called alternating voltage. Today, we are going to pull back the curtain on this fundamental concept. We'll explore what it means for voltage to alternate, and we'll decode the beautiful language of mathematics that describes it. By the time we're done, this diagram will no longer be just a collection of symbols and graphs. It will be a story, the story of the power that runs our world. So, let's begin with the title itself, alternating voltage. Imagine the electricity from a simple battery. That's called direct voltage, or DC. It's constant, steady, and flows in only one direction, like a river flowing steadily downstream. Alternating voltage, or AC, is completely different. It's more like the tide of the ocean. It doesn't just flow, it rises and falls, surging forward and then pulling back, constantly changing its strength and direction in a smooth, rhythmic cycle. The word alternating is the key. Now, how can we possibly describe something that's always changing? With this elegant little equation right here. This is the recipe, the master blueprint for alternating voltage. At first glance, it might look like something from a complex math textbook, but let's treat it like a sentence and break it down, word by word. First, we have V of t. The lowercase v stands for voltage. The little t next to it is incredibly important. It means that this voltage is a function of time. We call this the instantaneous voltage. Think of it as a snapshot. If you could freeze time for a single, infinitesimally small moment, a single instant, and measure the voltage, V of t would be the value you'd get. A millisecond later, that value will have changed. A millisecond after that, it will have changed again. This term represents the exact voltage at any specific point in time t. Next in our equation is Vm. The capital V tells us it's a specific, important voltage value, and the subscript m stands for maximum. So, Vm is the maximum voltage. This is the absolute peak, the highest point the voltage will ever reach during its cycle. It's also known as the amplitude. Imagine a wave on the ocean. The amplitude is the height of the wave from the calm sea level to the very tip of the crest. Our alternating voltage will rise to this peak value, Vm, and it will also fall to a negative peak of the same magnitude, which we call minus Vm. This value is measured in volts. Now we come to the most interesting part, sin, which is short for the sine function. This is the magic ingredient that gives the voltage its unique, wave-like character. Why a sine wave? It's not random, it's directly connected to how we generate most of our electricity. Picture a giant generator at a power plant. Inside, a magnet is spinning within a coil of wire. As one pole of the magnet moves towards the wire, the voltage climbs. As it spins to its peak position, the voltage hits its maximum. As it spins away, the voltage falls back to zero. Then, the other pole of the magnet swings by, and the voltage does the same thing, but in the opposite direction, it goes negative. This continuous, circular motion of the generator creates the perfectly smooth, repeating rise and fall of a sine wave. Inside the sine function, we have two letters multiplied together, omega and t. Let's start with the Greek letter omega. This represents the angular frequency. Now, that name sounds a bit technical, but the idea is simple. Think of it as the speed of the alternation. It tells us how rapidly the voltage is cycling through its pattern. A bigger omega means a faster cycle. It's measured in radians per second. A radian is just another way to measure an angle or a part of a circle, just like we can measure temperature in Celsius or Fahrenheit. A full circle is 2 pi radians. So, angular frequency tells us how many of these radians the wave travels through each second. And finally, we have our familiar friend, t, which simply stands for time, measured in seconds. This is the variable that keeps everything moving. As time, t, ticks forward, the value of omega t increases, and the sine function maps this progress into the beautiful wave you see on the graph. So, the whole equation, V of t equals Vm sine of omega t, reads like this: the voltage at any instant t is equal to the maximum possible voltage Vm, multiplied by the value of the sine wave at that point in its cycle. Now, let's see this story play out on the graph. The graph is a picture of our equation. The vertical axis is our instantaneous voltage, V of t. The horizontal axis, labeled omega t, represents our progress through one full cycle. We start at the origin, point 0. Here, both time and voltage are 0. As we move to the right, the wave begins to rise, smoothly and gracefully. It climbs higher and higher until it reaches its absolute peak. This peak, as you can see, is labeled Vm, our maximum voltage, our amplitude. After hitting the peak, the voltage begins to fall. It crosses the zero line again at the point marked pi, which is exactly halfway through the cycle. But it doesn't stop. It continues downward, into the negative territory. This means the voltage has reversed its polarity, and the electric current is now flowing in the opposite direction. It reaches a minimum point, a negative peak of minus Vm, before it starts to climb back towards zero. It finally completes one full, beautiful cycle when it returns to the zero line at the point marked 2 pi, ready to start the entire journey all over again. The time it takes to complete this one full cycle is so important that it gets its own name, the time period, represented by the capital letter T. It's the duration, in seconds, of one complete wave. Now, let's look to the right side of our diagram to connect these ideas with some very useful formulas. First, we see frequency, measured in hertz. While angular frequency, omega, is great for the math, in the real world, we usually talk about frequency in a simpler way, using the letter F. Frequency is measured in hertz, and it means cycles per second. For instance, in North America, the electricity from a wall socket is 60 hertz. This means that the voltage completes this entire up and down sine wave pattern 60 times every single second. It's happening so fast that our eyes can't see a light bulb flicker, we just see a steady glow. The formula omega equals 2 pi f is the bridge between these two types of frequency. It says the angular frequency is simply 2 pi multiplied by the regular frequency. This makes perfect sense. If one cycle is 2 pi radians, and you are doing f cycles per second, your total angular speed is 2 pi times f. The next formula, f equals omega divided by 2 pi, is just that same bridge, but looking from the other side. If you know the angular speed and want to find the cycles per second, you just divide by 2 pi. And finally, we have the beautifully simple relationship, t equals 1 divided by f. The time period is the inverse of the frequency. This is incredibly intuitive. If the frequency is 60 cycles per second, how long does one cycle take? It must take 1/60th of a second. If something happens 2 times per second, each occurrence must take half a second. The faster the frequency, the shorter the time period for each cycle. So, there you have it. We've journeyed from the invisible power in our walls to a single equation that describes its every move. We've learned that alternating voltage is a dynamic, wave-like force with a peak value called the amplitude, Vm. Its speed is described by its frequency, f, and the time for one cycle is its period, t. All of these terms and formulas are woven together, painting a complete picture of the energy that is the lifeblood of our modern technological world. Thank you for joining me on this exploration. I hope this has illuminated the fascinating world of alternating voltage for you. If you found this explanation helpful, please consider liking this video and subscribing for more journeys into the world of science and engineering. If you have any questions, please ask them in the comments below. Until next time, stay curious.